Okay, welcome back. We are at the point of the lecture where we discuss initial condition in the early universe. Inflation prepares the initial condition for all perturbations in a very specific way, such that all perturbations are stochastic. I think it's better if I point here, actually. They all have Gaussian statistics. They are all related to each other or all fully correlated through these adiabatic initial conditions. In particular, they can all be related to the curvature perturbation R. And so they are completely summarized by the primordial power spectrum of this curvature R, which is encoded in a function that we can take to be very close to k to the minus 3. And we parameterize the deviation from scale invariance with a power law k to the ns minus 1. Now comes a slide which is probably mathematically the simplest one of the lecture and conceptually the most important. To understand the evolution of perturbation, we need to solve a big system of coupled differential equations for each Fourier mode, giving the evolution of the deltas, the thetas, the metric fluctuation, everybody. And so when we have a big system, we have the general solution is a linear superposition of many modes. And for each mode, you have a solution which is multiplied by some constant. And in our case, saying that inflation has prepared the early universe in the adiabatic initial conditions means that out of all these solutions, we select only one. One set of solution of our equation of motion multiplied by one single constant of integration for each mode. And because we choose the curvature perturbation as a reference, we can use the curvature perturbation as this constant of integration. It means that for any perturbation, I call it generically A would be one of the metric fluctuation, density, velocity, photon anisotropy multiple, etc. Any function that depends on time and space, or in Fourier mode, space on time and Fourier modes, like here. For any of these functions, I can write my solution at the time eta as a function which is the solution of the equations of motion starting from adiabatic initial condition, normalized to a constant of integration that I can choose to be the curvature perturbation at initial time for this Fourier mode. Okay, so when you have a harmonic oscillator, you can write your solution as cosine A times sine B. Here you have only one mode, like in cosine times A. The cosine would be the solution of the equation of motion, and the A is now this constant of integration. That's absolutely crucial. Then let's look at the argument. I'm trying to find the general solution of a perturbation at some time and for some Fourier mode K. And this depends on my initial condition for the curvature for the same Fourier mode K at some initial time eta initial. Actually, because curvature perturbations are constant in time in the super-Hubble regime, this Ni is irrelevant. I could choose any time such that my fluctuation is in the super-Hubble regime, and I could denote R as just a function of my Fourier mode K. And now this is supposed to be a solution of the equation of motion, fulfilling the adiabatic initial condition and normalized to R. So it should depend on time, of course. And it should depend on K, but not on the vector K, because I'm working in a statistically isotropic universe. So the equations of motion or the primordial power spectrum, they are a function of the wave number K, but not on the direction of the mode. So the solution of the equation of motion is only a function of the wave number K. Another way to define this quantity is to say, okay, this quantity is a ratio of a perturbation at time eta divided by the curvature perturbation at initial time. So to find this function, you would solve the system of coupled differential equation normalized to adiabatic initial conditions with R set to 1. And we are going to call this set of functions the transfer functions, because they show you how you transfer your solution from initial time to a later time. I've highlighted things in colors here with the following meaning. We have to remember that the curvature perturbation of a given Fourier mode is a stochastic number. Inflation doesn't predict the true value of R for each Fourier mode. It predicts only its statistical distribution. So this R should be seen as a stochastic number, a random number with a given probability distribution. There is no need to see the transfer function as a random number. On the contrary, the transfer function is a solution of classical equations of motion, which tells you that if you select a value of R, you multiply by t, you get this fluctuation today. If you start from a twice bigger R, you multiply by t, you get a twice bigger A today. So it shows you how you are going to transport the initial random variable into a random variable at a later time. So the functions that are in green and that depend on Fourier modes should be seen as stochastic Fourier modes or stochastic number, but the transfer function is completely deterministic. So this transfer function gives you the transport of probability. There is a linear transport of probability. Another way to see this relation is that at initial time for our probability, for our perturbation A, the perturbation A has an amplitude governed by a probability distribution, which in our case will be a Gaussian. At a later time, this is another time, A also has a probability distribution. The transfer function tells you how you go from here to here. If you start from 0, you get 0. If you start from a value of A, here you will get the same value multiplied by some number. If you start from a twice bigger value, you will get the previous value multiplied by 2. Etc., etc. So the transfer function tells you how you transport probability from initial time to a later time. And this linear transport of probability cannot change the shape of the distribution of probability. It can only stretch this axis. So if you start from a Gaussian distribution, you must continue with a Gaussian distribution at any later time, as long as you are using linear theory, because this way of decomposing the solution is really the distinct sign of linear theory. And in particular, it means that the variance at a later time is related to the variance at an initial time very easily. I just need essentially to square this relation, and I will see that the variance of A evolves like the square of the transfer function times the variance of R. We do it explicitly. We write our correlator for the perturbation A at some time between a mode K and a mode K prime. And we replace A and A star by the expression we found before. Then inside the correlator, we will have two transfer functions and two R. We can move the transfer function outside. This is what I did here. Because the transfer functions are deterministic numbers, so they can be moved out of the correlator. But the R are random numbers, so they stay in the correlator. What I get here is the power spectrum of R. So I can write the power spectrum of A at a later time like the square of my transfer function times the primordial spectrum of curvature, and I always have the Dirac delta function which enters here. Small detail on the notation. Here I denoted the transfer function as A. Here I had a more complicated notation, TA. So this is something that people do very commonly. If for any perturbation A, we had to write the transfer function as TA, all notation would be very heavy. For instance, when I have a theta L here, I would need to write theta of L. It's not really needed to keep this specific letter to denote that it's a transfer function. It's clear from the fact that it depends on K, that it's a deterministic number. So what people do very often in a course or in an article about cosmological perturbation is that when you write a perturbation with a vector, you immediately understand that this is the stochastic number. When you write the perturbation with a Fourier mode, you implicitly understand that it's a deterministic transfer function. So to make lighter notation, I switched from TA to just A, and it's clear from the argument that this is a transfer function, while this is a stochastic perturbation. And that's why when I took the power spectrum, I had A star here. This is incredibly powerful. It's the reason for which linear perturbation theory is so much simpler than nonlinear perturbation theory. The only thing we need to know is a variance of different types of perturbation, the density of photons, the density of matter, etc. And in linear perturbation theory, we can always decompose the variance or power spectrum of this perturbation in two terms. One term is a primordial power spectrum. The other one is a modulus square of the transfer function. To get this, you ask a specialist of inflation to compute the primordial spectrum for a given model, or you just rely on the standard parametrization in terms of a power law. To get this, you need to integrate differential equation, and that's the true purpose of Boltzmann codes like CMB or class. They will do this integration for you, starting from appropriate initial condition, which are R equal 1. You will get this, you will square it, multiply by the primordial spectrum, and you will get the variance of any perturbation. So this is extremely, extremely powerful. It's the whole logic of linear cosmological perturbation theory. Let me check my next slide. Yes. So until now, what I said is really part of the common knowledge of any respectable cosmologist. And for you, it should be completely clear. And in particular, if you are not completely familiar with this, you will struggle to go to the level of nonlinear perturbation theory. So now I will climb a step and I will enter into a more specific consideration about the CMB. Do you have questions so far? Yeah. Yeah. Okay, I had forgotten this. I remember well that in the older code, CMB fast, everything was normalized to psi equal 1, but I would think that in CMB, it's also normalized to R equal 1. Ah, no, I know what you have in mind. Sorry. Yes, internally in the two codes, the transfer functions are the same. But there is something that COM calls a transfer function, and which you can get in output. And this something is multiplied by powers of k for some historical arbitrary reasons. So both code internally define the transfer function from the condition R equal 1, but at some point when writing some output, COM multiplies this by some k to the 3 factor just for some arbitrary reason. Yeah. Good. Okay, so now we go into more specific CMB stuff. We saw the visibility function. We said that it has a narrow peak close to recombination. If we would idealize this peak as a Dirac delta function, all photons would decouple at the same time, then they would travel in straight line. And so all the photons that we would see here today, being the observers and looking in different directions, would have traveled over the same amount of time, the time between recombination and today. And because they all travel at the same speed, it means that they had their last interaction at the same distance from the observer, so they all seem to originate from a perfect sphere. So when we observe photons, we observe a picture of the universe in a spherical cut of our space-time, which is the last scattering sphere. The quantity we observe here is a temperature in each direction. And we are going to expand it in perturbation by introducing the function delta T over T bar, which is dimensionless, and T bar is the average temperature averaged over all directions of observation. If we try to relate the observable delta T over T to the photon anisotropy that we defined before, this would be equal to the photon anisotropy function today at our location in space, which I wrote here as the origin of space-time. It's an arbitrary choice. And if I look in a direction n, it means that I look at photon propagating in the direction minus n. So there is a minus n here. Now, this delta T over T is a function of two angles. So now I should use, if I want to decompose it in modes, I should use a standard spherical harmonic decomposition and translate my map into coefficients ALM. In parallel, we have seen that the theta can be expanded first in Fourier and then in Legendre space to give some theta L coefficients. So if I do the transformation of this variable and also the transformation of the delta t over t, they are a bit similar. So there should be a relation between the multiple theta L in Fourier space and this ALM. It's a small mathematical exercise to find this relation. You can also invert it, and you get this equation. This is shown in many books, textbooks. It takes only 4 lines maybe to show it. And after inverting, you find that each coefficient ALM is given by an integral over all Fourier modes of your Legendre multiple of the Fourier mode theta L evaluated today for the mode K, multiplied by a spherical harmonic evaluated in the direction of the Fourier mode. Now, let's remember that all our fluctuations which depend on Fourier mode should in fact be seen as stochastic numbers. This means that ALM, which is a sum over the theta L, is also a stochastic number. And moreover, it's a sum of Gaussian distributed number that will give you another Gaussian distributed number. So ALM will be a Gaussian distributed number, which means that the interesting information is contained in its variance. And so we can compute its variance by starting from this correlator. We replace each of them using this relation. We get 2 integrals over a k and a k prime. But then in the correlator, if we replace the stochastic number theta L by the product of the photon transfer function theta L of k times the primordial spectrum for the mode k, we will have 2 transfer functions, and we will have the correlator of 2 R's. We can replace the correlator of the 2 R's by the primordial power spectrum multiplied by a Dirac delta function, which allows us to get rid of one of the 2 integrals over k. We carry on a little bit. We integrate over angles. We use the orthogonality condition of the spherical harmonic. And after, again, 4 or 5 lines of calculation, we find this nice relation which tells us that the variance of each ALM is 0 if the L and M's are different. And this is a counterpart in harmonic space of the fact that in Fourier space, the variance of the curvature variable is 0 if k is different from k prime. This translates in the similar way in harmonic space. So we have this Kronecker symbol. And then if we correlate ALM with itself, we get a non-zero variance, which is found to be an integral over the wave numbers k of the photon transfer function for the wave number k and the multiple L squared, evaluated today, times the primordial spectrum. And this variance plays a very, very big role in cosmology because it is the quantity that allows you to compare theory and observations. Why? From the theory point of view, we have such a relation, so we see that we can compute this variance. We can use our Boltzmann code to get this transfer function, our inflationary model to get P of R. We can carry the integral and get the variance. And if we are observers, we are going to see that we can guess this variance also in an empirical way. Note that the variance that we get only depends on L. It's explicit from the right-hand side. In the right-hand side, you have no M dependence. Again, this has to do with the statistical isotropy of the universe. In a multiple, the number L tells you something about the scale of the variation of the pattern on the sphere, while the variable M gives you an information on the way in which you orient your multiple. And this orientation should the variance, the statistical properties of the ALM should be the same in all directions, should not depend on the orientation of the multiple, but only on the scales that you are looking at. So it's not a surprise that it depends only on L and not on M. So you can call this variance CL. And this will be our CMB temperature power spectrum. Now, why can you estimate it from the data? What the data gives you is just a set of ALM. And when you have one measurement of a stochastic variable, it's very, and you don't know what is the distribution of probability of the variable, it's very difficult to guess it. Even if we know that each ALM has a Gaussian distribution of probability, if we get one measurement of one ALM, we don't know much about the true variance of this quantity. It's exactly like if I give you a dice and I tell you the dice is biased, but you have to find out how. If you throw the dice 1, you have one realization of the probability distribution that you want to measure, and you still don't know this probability distribution. But what you can do is throw the dice many times, and after a very big number of time, you are going to be able to track first the mean, and then the variance, and then the full distribution of probability. So can we throw the dice many times here? Not in the sense that we can repeat our CMB observation and see some different ALMs. We see only one realization of the theory. That's a big limitation of cosmology. However, we can exploit the fact that all the ALMs with different M's but the same L have the same variance. And so if I measure all my ALMs with fixed L and with M varying between minus L and L, it's like if I would have thrown my dice many times, and I can start to estimate the variance. And I can build an estimator of this variance by just taking the average of the ALM squared. And in this average, I divide by 2L plus 1, which is just the number of values of M for a given L. And this will give me an estimate of my variance. Of course, when L grows, I have more independent realization. So my estimator will be closer to the true value. And to check this mathematically, I can do an exercise of statistics. I can compute, given this definition of the estimator and considering the ALMs as Gaussian random numbers, I can compute the typical variance between the true CL of the theory, the true CL of the ALMs, and the estimator inferred from this relation. And after using Wick's theorem and a few lines of calculation again, I find that this variance is given by the CLs themselves squared times 2 over 2L plus 1. And this prefactor decreases when L increases, simply because when I look at a big L, I have more independent realization of my underlying probability distribution. So I have a good chance to get a precise guess of the true cosmic variance. And so this deviation goes down. And this is exactly what we call cosmic variance. And we can see it very well when we plot CMB data. Here, this is a version of some old Planck data where each black point is a measurement of a CL at a given L. And you can see that on small L, the scattering is large, and then the scattering goes down as a consequence of cosmic variance. So cosmic variance is not a problem, but it's like a theoretical error, and it means that even in a perfect theory, we cannot expect our theoretical CL to go through each individual point. They should go through the point with some typical dispersion of the points around the true theory given by cosmic variance. So you should never try to overfit CMB data with a lot of freedom in your curve. Okay, so as a conclusion of this slide, the CLs are a quantity that we can both predict theoretically and estimate observationally. So this is a key quantity if we want to extract cosmological information from the CMB by just fitting the theory to the observations. And now we are going to enter in the stage of describing really the underlying physical mechanism that will allow us to understand the shape of the CL power spectrum and how the CL depends on my physical assumptions and my cosmological parameters. So I have a limited amount of time. I give a version of this part in different courses in more or less time. In my full master course in Aachen, this would take about 8 hours, and we're going to do it in about 2 hours. So I make a choice on what I can say and what I should not say. And I hope that this choice will be helpful. The most difficult is that we need to find a solution to the Boltzmann equation. So a full analytic solution to the Boltzmann equation for photons would be very difficult to find. What we can find is a formal solution. Formal solution, you know, it's an integral solution such that you still don't know what the solution is, but you understand its structure. And there is a beautiful formal solution for the Boltzmann equation of photons, which gives you theta for each multiple L and each Fourier mode today. I have put here a little vector between parentheses because this relation that we will describe is true both at the level of stochastic numbers or at the level of transfer function. It depends if in the other perturbation that you find here, you put a vector or you put a wave number. So this solution was found by Matías Aldariaga when he was doing his thesis in Buenos Aires with his supervisor, Diego Harari. And it's called the line of sight integral, which is a bit confusing because this solution holds in Fourier space. And when you think of a line of sight integral, it's in real space. So the reason for the name is that at an earlier stage, we could try to find a formal solution of the Boltzmann equation in real space. This is easier. It gives you a very nice and famous solution called the line of sight integral. And I'm just keeping it for time reasons, because otherwise it would add, I don't know, 20 extra minutes. And I go directly to the Fourier version. However, the solution in real and in Fourier space look pretty similar, and that's why the name of the solution in real space has been also adopted for the solution in Fourier space. So I will call it the line of sight integral in Fourier space, even if the name sounds completely absurd. Okay, so let's look at this formal solution. Like usually formal solution, it gives you the solution at the time you are interested in, which is today, as an integral over earlier time from some initial time, doesn't matter, until today. So it's an integral over conformal time, and then we have three terms in our integrand. And in each of these terms, we have the same structure. We have a function of time that we already reviewed when we looked at the thermal history of photons. Then we have perturbations or transfer function. It's as you like, it's a question of normalization. And then we have these funny functions which are spherical Bessel function. And we are going to understand this structure and the meaning of each term over the next 30 minutes. In summary, we could say the following. We could say that we have a sum over physical effects which are relevant at the time described by the green functions, which leave an impact on the photon anisotropies described in Fourier space by the pink functions. So the pink functions will be the perturbation that are the different sources of the final photon anisotropy that you want to measure. And these Fourier modes are projected to multiple space according to the blue factors. So that's the deep meaning of this relation. But now we are going to inspect it with calm. And we are going to wonder first, why the hell we have spherical Bessel functions here? How do they appear? So they appear every time that you have a Fourier mode propagating in a three-dimensional space-time. And instead of doing observation in this full three-dimensional space-time, you do your observation in a sphere, which is a cut in your space-time. And this cut goes through the maxima and the minima defined by the Fourier mode. So I tried to plot this symbolically here. So this box is supposed to be a box in the universe filled by only one Fourier mode. You see that the wave vector is vertical, and so in horizontal cuts, you have maxima in red, minima in blue, and this is supposed to follow a cosine structure. The wavelength of the mode is given by the separation between two adjacent maxima or two adjacent minima. And then suppose that you observe these fluctuations, not in 3D, but on a spherical cut that I have drawn here with a given radius. Then your Fourier mode, so you will measure fluctuation on the sphere, and you can expand the fluctuation you measure in multiples. And depending on the value of the multiples, some multiples will be excited by the structure of the Fourier mode, and some will not be excited. You should think also that the true picture is three-dimensional. And if you think of the sphere, this sphere has an axis of symmetry, which is here the vertical axis in my drawing, because it's the axis of the Fourier mode. It's easy to understand that the multiple, which will be the most excited, is a multiple such that the angular separation between a maximum and a minimum is given by this angle, the angle under which you see half a wavelength. So why half? Half a wavelength because it's under half a wavelength that you have a separation between a maximum and a minimum. Okay, and when you talk about a multiple L, L is related to an angle theta through the famous relation theta equal pi over L, where theta is the angular separation between one adjacent maximum and minimum. For instance, for L equal 2, you get theta equal pi, and the separation is indeed 180 degrees. For L equal 2, the quadruple, the separation between maxima and minima is 90 degrees, or pi over 2. So this multiple is the one that is the most excited by this Fourier mode. To understand why, you have to think in three dimensions. This Fourier mode excites this multiple all around the equator. Here, there are maxima and minima that I see under a larger angle, but only on a small surface, because I'm not going around the full length of the equator. So already from this diagram, you see that my Fourier mode will excite other multiples, in particular here, multiples corresponding to a larger angle and a smaller L, but the excitation will be reduced. And finally, you could think also that this Fourier, the same Fourier mode, the same wavelengths, will excite also much larger values of L, which correspond to harmonics. If I look at a multiple such that I would have here a maximum, a minimum, a maximum, and a minimum again, this mode will also be excited. It will be one of the harmonics. Now, the spherical Bessel function encodes exactly these projection effects, and we are going to see why. So as we say, the main contribution to the multiple from this Fourier mode should be encoded by the equality between the angle theta and the half wavelengths, but with a relation which is valid in cosmology, which tells you that if I see this half wavelength under an angle theta, then theta must be equal to the half wavelength divided by the angular diameter distance to the sphere, where the angular diameter distance here is the radius of my sphere. And if I replace theta by pi over L, I get this nice equality. Pi over L, where L is the most excited multiple, must be equal to lambda over 2 divided by the angular diameter distance to the sphere. Now I use my knowledge of cosmology to replace lambda by the scale factor times 2 pi over k, and to replace dA, if I assume a flat universe, by the scale factor times eta 0 minus eta. If this denominator is not clear for you, I remind you that dA is given by an integral by the scale factor times an integral of dt over a in a flat universe, without any sign or hyperbolic sign. And dt over a is d eta. So then you have an integral over d eta, which just gives you the difference between eta at emission and at reception. Here I assume that I observe Fourier modes that live at the time eta, and the observer lives at time eta 0. So when I express my physical wavelengths, I replace it by a at the time eta, at which the Fourier mode lives, times 2 pi over k. And when I express my angular diameter distance, I integrate my conformal time between the time of emission of the signal, which is eta, and the time of reception, which is eta 0. So this should be clear, and now I see that I can simplify by the scale factor, and I get a relation which is just L equal K eta 0 minus eta. So the main contribution, the mode which is the most excited by my mode K, should be the multiple L equal to K eta 0 or minus eta. So with this geometrical reasoning, I am establishing a correspondence between the multiple measured by the observers and the Fourier mode on the last scattering surface that excites these multiples. And in an ideal world, I would expect a one-to-one correspondence. I would expect Fourier modes of one wavelength, one wave number, to create an isotropy in my CMB map that I see for one multiple. It's not exactly the case because of what we said. There are also a role of larger angles, and there are also some harmonics. And this is encoded in this Bessel function. The Bessel function, I plot here J10 as a function of x, has a structure where it is vanishing, and then it rises with a maximum close to x equal L. Here it would be 10. And then it has damped oscillation. So look at the factor that we have here. We have the Bessel function JL of K eta 0 minus eta. So the peak of this function should be when L is equal to K eta 0 minus eta, which is precisely this relation. So the peak of the Bessel function is indeed telling me that I have a one-to-one correspondence between K modes and L multiples. The fact that this is not a Dirac delta function comes from the other effects that we described. Here we have a smooth decrease, accounting for the fact that this mode is also exciting larger angles, which are smaller multiples. And this series of peaks correspond to all the harmonics that are also excited by the same Fourier mode. In summary, we now understand that this Bessel function is a projector from the Fourier mode, which is a space in which this perturbation lives, to multiple space, which is a space in which this is observed. So now we go back to our three effects, and we will try to understand them one after each other. And we start from the first line, which tells us that our observable photon multiple theta L gets a contribution from the Fourier mode theta 0 plus psi at some time eta, multiplied by the visibility function at time eta, and multiplied by this kind of projection kernel from Fourier to harmonic space. And this term is much easier to understand if we remember that G is very peaked near the time of photon decoupling. If you remember, G had two peaks, one at recombination or photon decoupling and one at reionization. At the beginning of this lecture, we will deliberately ignore reionization to make things simpler, and I will reintroduce the effect of reionization in a single slide near the end. So I assume that G eta is very peaked, and I take the approximation in which the peak is so narrow that I replace it with a Dirac delta function of eta minus eta of photon decoupling, which means that I really see photon coming from a sphere and not from a thick shell. And in this approximation, I would expect this projection effect that mode K project to multiple L equal K eta 0 minus eta dec. And indeed, this is exactly what happened. If I replace G by a Dirac function of eta minus eta dec, I can carry this integral. The visibility goes away because it's normalized to 1. And here I have my Fourier mode living at the time eta dec, and for a wave number k, while here I have this projection kernel, which projects my k to a given L. But now I should not use an arbitrary value of time here in the projection. I should use eta dec because I'm selecting perturbation that live at the time of decoupling. And with this in mind, I realize that my theta L today comes from the monopole of the photon anisotropy at the time of decoupling, corrected by the gravitational potential for the same mode at the time of decoupling. The meaning of the first term, which is called the intrinsic fluctuation, is the most obvious one. It just tells me that if in the early universe I have an overdensity, which would be an excess of theta 0, I should observe, after the projection, I should observe also an overdensity. Overdensity on the last scattering sphere project into observable overdensity. Underdensities on the last scattering sphere project onto observable underdensity. You could imagine even that this effect should be the only one. Naively, you would expect this is the only effect, such that the CMB map we see just reflects what was the density, photon density pattern on this sphere at the time of last scattering. But it's not the only effect, and we already see here at the level of the first line, because this intrinsic fluctuation is corrected by a term psi. Why? Why? Because photons can experience gravitational Doppler shifts. So this is illustrated by this figure. We are the observer, we live on the right. We look at photons coming from different points on the last scattering surface, and this little arc is supposed to be just a little arc of the full last scattering sphere. And on points of the last scattering sphere, we find photons which are overdense, so with an excess of temperature, and photons which are underdense with a deficit of temperature. However, these photons are coupled to gravity. There is always a relation between the gravitational potential and the overdensity given by the Einstein equation. And so I know that when I have a photon overdensity, I have a gravitational potential well. When I have a photon underdensity, I have a maximum of the gravitational potential. When photons leave an overdense region, they need to climb out of a gravitational potential well. So they will lose energy. And it will make them colder. While when a photon leaves from an underdense region, it gains momentum by rolling down a gravitational potential hill. It gains energy. So these two terms will always be competing with each other. They will always play in different directions. And the big question is which one wins? If this is a small correction and this term wins, we get a faithful image of the CMB last scattering sphere. If this is a huge correction and this term wins, we will see a negative image of the last scattering sphere. What we will see as hotter photon will be photon originating from an underdense region. There is no simple question to the answer who wins, because we are in Fourier space, and the relation between theta 0 and psi depends on the wave number k. So we will get one answer if we only think about the contribution of large scales, and another answer if we only think about the contribution of small scales. Before, we have seen the relation between the gravitational potential and the density fluctuation on super Hubble scales. It was part of what we wrote as a diabatic initial condition. And we said that minus 2 psi is equal to delta tot. But for photons, delta tot is 4 theta 0. And the relation given by the Einstein equation on super Hubble scale becomes psi equal minus 2 theta 0. This is valid for super Hubble scales. And if I replace psi by minus 2 theta 0 here, I see that this term wins. It's twice bigger in absolute value. And so if I would only look at the contribution from large scales, I would conclude that this correction is huge and that I see a negative image of the CMB. And in fact, the very large wavelengths are seen by us today under very small multipoles. This comes from the one-to-one correspondence that we described before. So when we look at the CMB map for very small multipoles, meaning very large angular separation, we see mainly very large modes that were super Hubble at the time of recombination. And so we see a negative image of the CMB. So take an image of the CMB, Close your eyes a little bit, you get a smoothed image of the map. And for this smoothed image, you can really think that a big red pattern corresponding to hotter observed photon was in fact a big underdense region at the time of photon decoupling. But again, this is scale dependent because on small scales, this does not hold. It's replaced, in fact, by the Poisson equation. And we will say later that on small scale, psi decays, it's negligible. So on small scale, this correction disappears. And the little dots that you see in your CMB map give you directly the intrinsic fluctuation on the CMB last scattering sphere without this inversion. So this correction here, which is a gravitational Doppler shift, was first found by Sachs and Wolf, two cosmologists working in California in the 60s. And so it's called the Sachs-Wolf correction. Some people call the full sum the Sachs-Wolf term. Some say that only this is a Sachs-Wolf term. That's just about nomenclature. But this is a Sachs-Wolf effect. And I hope that we understand now the first line. So if there is no question, I will go to the second line. Yeah.
Affected by the fact that there is some depth to the surface of last scattering?
Yes, very good. We will come to it later on. Yeah, there will be a smoothing from this. Yeah. Okay, second line. So you see that in the second line, we have again the visibility function. Nice. We can assume again that it's very peaked, think that it's a Dirac delta function, carry the integral out, and we are left with the baryon velocity divergence evaluated at the time of decoupling, projected through this Bessel function. And there is a prime here. Yeah, it's a detail that we don't have time to explain. There is a prime which comes from the structure of this term. This term has to do with a gradient, and this has consequence when you go to Fourier space. It doesn't matter. In fact, the shape of JL prime is almost the same as the shape of JL, and you can think of it as being a slightly modified version of this projection kernel without any consequence. So the second line tells us that we also get a correction to the photon anisotropies that we see that comes from the bulk velocity of baryons projected in the usual way from K space to L space. In real space, this term that we see here, K minus 1 theta B, would come from the scalar product between the direction of propagation of the photon and the bulk velocity of the baryon, or at least its scalar component. Then if you realize that the scalar quantity can be encoded into its divergence, the divergence in Fourier space will give you the velocity divided by k, and this is how you get the k minus 1 here. So this term physically comes from a term in real space, which has to do with the bulk velocity of the baryon. And so unsurprisingly, we can conclude that it's a true velocity Doppler shift. It comes from the fact that the photon that we observe are emitted by a tightly coupled photon-baryon fluid before recombination, and this velocity has random orientation. And so if by chance you see a photon coming from a region where the fluid was moving away from you, then this photon will be redshifted by the Doppler effect. If the velocity is pointing at you, the photon will be blue shifted by this additional term. And this term is really, this effect is in addition to the fact that you had a given value of the temperature and of the gravitational potential here. So it needs to be taken into account additionally. So it is a Doppler correction. Okay, that should be easy, I think. The last term is a little bit more subtle. The last term is an integral. I go back here. It's an integral over the exponential of minus tau times two partial derivatives of phi m psi times, again, our Bessel function evaluated at time eta. So I cannot replace this by a Dirac delta function. On the contrary, if I want to work in some approximation and neglecting reionization, I can say that at any time between now and recombination, the optical depth is very small. If the optical depth is very small, this factor is almost 1. And then before recombination, the optical depth is very big, and this factor kills the contribution. So exponential of minus tau can be considered as 0 before decombination and 1 at later time, which means that my integral just becomes an integral over these terms here by integrating from decoupling until now. And so this term has to do with what happens to my photons between the time of decoupling and today. And in those time, photons are gently traveling along their respective line of sight between the last scattering sphere and today. And then this term suggests that if at some time eta between decoupling and today, I have metric fluctuation with some time derivative, then my photons should be affected. And it makes sense because while my photons travel, they continuously travel through maxima and minima of the gravitational potential. I will work in the approximation in which phi is equal to psi, and they both account for the gravitational potential. So the photon is continuously redshifted and blue shifted. And maybe I need to know the full history of these blue shift and red shifts in order to compute my observable signal. It's not really the case because we are very, very fortunate, and I will explain why. But first, let me tell you, it is clear from this equation, already at a mathematical level, that in a universe where phi m psi would be non-zero but static, you have perturbation in the universe, but they don't evolve with time. With such static metric fluctuation, the partial derivative vanish, and in this case, you can show that this effect is conservative, as very often with propagation in a gravitational environment. It's conservative, meaning that, yes, the photon gets blue shifted or red shifted, but you only need to know the value of the gravitational potential at emission and reception, and the net effect will be given by the difference between the two. And in fact, we already took this effect into account because when we wrote the Sachs-Wolf term, this psi was a gravitational potential at the time of emission. So the psi at the time of emission, which is psi dec, was already taken into account in our Sachs-Wolf term. The psi at our location does not matter. Why? Because what this reasoning says is that the CMB map that we observe depends on the value of the gravitational potential at the location of my South Pole telescope, for instance. But this value is just one number. It's very small, and it does not depend on the direction in which I'm looking. So it does not introduce anisotropies, and it will be automatically effectively incorporated in my averaging over all direction to get a T-bar. So if phi m psi are static, we have already taken them into account, taken this effect into account when we describe the Sachs-Wolf effect. However, when phi m psi explicitly depend on time, our universe does not only contain perturbation, but these perturbations evolve. Then the effect is no longer conservative, it's cumulative. It needs to be computed by integrating along the line of sight. And in particular, if a gravitational potential well is getting deeper and deeper due to structure formation. When the photon falls in the potential well is still small, and the photon gains a little bit of energy. When it leaves the potential well, it needs to struggle a lot more because the potential well is already deeper if some time has passed by. So we understand this net effect in this way. And as a consequence, which one is the next slide? Yeah, as a consequence, to capture this effect, we need to integrate over all possible time. Actually, I forgot to keep an integral here. It's unfortunate. So I go back to here. We need to integrate over all possible time over the partial derivative of the metric fluctuation with respect to time, evaluated at time eta, multiplied by the projection kernel, which is relevant at time eta, and which has this running value of eta in the argument. And this gives you all the effects that contribute to the final theta L. So there is a Sachs-Wolf effect, there is a Doppler effect, and there is this other effect, which is called the integrated Sachs-Wolf effect. We will see when this integrated Sachs-Wolf effect is relevant, but as a spoiler, I can tell you that in most regimes in the evolution of linear cosmological perturbation, this partial derivative of the metric with respect to time will be negligible. That's very nice. It means that at the end, this integrated Sachs-Wolf effect will play a very small role. Why is it nice? It's nice because it means that the third line only brings a small correction, and that what we observe is still mainly a picture of the CMB patterns on the last scattering sphere. If phi m psi were varying a lot at all times for all scales, the third term would maybe dominate, and then our CMB observation would not tell us things about the last scattering sphere. They would tell us things about this complicated random metric fluctuation in the nearer universe, and that would be less interesting. There would be less interesting information to extract from it. Okay, so now we understand what this equation means, and I remind you that the motivation for doing all this discussion was that if we want to compute the CLs, to predict the CLs in a given theory, the hard job is to compute this theta L. Computing PR is easy. There is a parametric ansatz, but computing theta L can be tricky. And now we have a nice way to compute this theta L by performing this integral. And we see that if we want to understand the shape of this theta L, with maybe some analytic approximation, we don't need to compute that much. We need to compute the shape of the theta 0 and psi transfer function just at decoupling. Then we need to compute the shape of the baryon velocity just at decoupling. And then we need to compute the shape of phi m psi and their evolution with time at all times between decoupling and today. If we understand qualitatively the shape of all these transfer functions, we will put them together, shake a bit, and we will have an intuition on what should be the shape of theta L. We will put the result into the integral, and we will have an intuition on what will be the shape of the spectrum CL. And this is our program for the next minutes. This is what we are going to try to do. Everything clear? So I will go step by step. I will first talk about the evolution of these relevant quantities as a function of time for one mode. And we will try to understand why this solution evolved, because of which physical effect, etc. And when we are done for one mode, we will look at this evolution for all modes. And then we will be in a situation to conclude and to derive the shape of the CL and of its different contributions. And we have until 6, right? Half an hour. Very good. All right. So let's proceed. And what we need first, if we want to understand the evolution of solutions, is an equation of motion. And the most important variable in the game is still theta 0. The term theta 0 is a dominant term. So my dream is to have a nice equation of evolution for theta 0, in which I could discuss some approximation for the solution. Theta 0, in principle, is governed by a complicated Boltzmann equation, which is difficult to solve. The magic is that we can gain some understanding by working in a limit, which is called the tight coupling approximation. The tight coupling approximation is simply the approximation in which the Thomson scattering rate is much bigger than the Hubble rate. So We have very, very efficient coupling between baryons and photons, and this will make our life simpler. Why? First, if I am in this regime, my photons are in thermal equilibrium. And in thermal equilibrium, we have seen this morning that the density is related to the monopole of temperature in this way. And we can say something more. We can say that because we have thermal equilibrium between baryons and photons, we have also this relation between delta B and theta 0 that we have seen also this morning. So we have a relation between delta gamma and delta B. They are not independent of each other. The next thing we see in the tightly coupled approximation is the fact that the dipole theta 1 is related to the velocity of the photon. In fact, the velocity of the photon must be the same thing as the dipole of the photon anisotropy, because the velocity of the photon manifests itself through a Doppler shift of the photon anisotropy. So I have a relation between the velocity of the photon and the dipole of the photon anisotropy, which is given by this. If I am in the tightly coupled limits, I have seen this morning that my Thomson scattering term forces photon and baryons to get aligned on each other, which means that theta gamma and theta B must be equal to each other. And additionally, this Thomson scattering rate and the Boltzmann equation force higher multipoles to vanish. You remember this morning when we said the role of Thomson scattering is to isotropize the photons in the frame of the electron. So all higher multipoles vanish. So in the early universe, all these relations hold. And that's very convenient because in general, my equations of motion should be given by the Boltzmann hierarchy for the photons, and then the continuity and Euler equation for the baryons that I need to solve jointly because of Thomson scattering. Using this relation, I can cut the Boltzmann hierarchy at L bigger than 2, and I'm left just with 4 equations, which are the continuity and Euler equation of the baryons, the continuity and Euler equation of the photon. I have 4. Thanks to these inequalities here, I can go from 4 to 2. I have now 2 first-order differential equations. From this, I can get a single second-order differential equation for one of the variable, and the nicer is to select theta 0 as our master variable. This is how, in principle, you can get a second-order differential equation for theta 0, which is exact in this tightly coupled limit. And this equation is made up of 6 terms. It looks a bit scary at first sight, but we will see that the terms are pretty intuitive. The most obvious and important one are the second derivative and this effective mass term k square cs square theta 0. Suppose that we would have no gravity, no expansion of the universe. We would have only these terms governing the evolution of our photon. We would have theta 0 prime prime plus k square cs square theta 0 is equal to 0, where cs is the sound speed of my baryon photon fluid. So why is this term so obvious? So first, we try to guess why physically, what is the physical reason for this effective mass term? And because there is a sound speed here, we understand that cs square is delta p over delta rho. It's a complicated ratio. But in theta 0, the monopole is related to the density fluctuation. So in the theta 0, I have a delta rho. And the delta rho, which is here in the numerator and here in the denominator, simplify. And in fact, this product is related to delta P, the pressure fluctuation. And in front, I have a k square. So immediately, I understand that in real space, it would be a Laplacian, a Laplace operator of the pressure perturbation. Now, if you have done a little bit of fluid mechanics, you know that in fluid equation, very often, you have the Laplacian of the pressure that appears. It just accounts for pressure forces. So this term is a term of pressure forces. So because our photons are ultra-relativistic, they have quantum pressure, like P equal 1/3 of rho. And this is why you have this term at the end. I will give details on the exact shape of CS square, but mainly it comes from this quantum pressure of the photons. So suppose there would be no gravity and only pressure, we would have these two terms equal to 0, and the solution would be like a sine or a cosine. If your Fourier mode oscillates like a sine or a cosine, or say just an exponential of some complex phase. If you go to real space, you need to multiply this oscillating solution with your factor exponential of ik times x, and you get the full structure of a plane wave. So if we had only the pink terms, the solution in Fourier space would be oscillatory, and in real space, it would be plane waves. Of course, the explanation is that when you have a fluid with pressure, you have a propagation of plane waves. You don't need gravity for this. The propagation of sound in the air only comes from pressure and not from gravity. And this is what will happen in the early universe. In the early universe, you create overdensities. Well, inflation creates overdensities. And then when pressure force become important, and then there is a causality argument that it will take place only on sub-Hubble scale, then this overdensity will travel in the form of pressure waves or density waves. It's the same. And this is the famous acoustic oscillations, which would show up as plane waves in real space and as oscillations in Fourier space. So now we see where the famous acoustic oscillations come from. If we refine a little bit on the expression of the sound speed square, it's delta P over delta rho, but computed for the full photon baryon fluid. So there is a small subtlety from the fact that the photons have quantum pressure, but the baryons have negligible pressure because they are non-relativistic. And you need to combine the two, which is not so trivial because radiation photons have a density scaling like 8 to the minus 4, baryons like 8 to the minus 3. So they play more and more role in the fluid. And this means that during radiation domination, the sound speed is the same as in a pure photon fluid. But at the beginning of matter domination, when baryons become important, you have less pressure effectively in the full fluid, and the sound speed decreases. And when you compute it, a very simple calculation shows that it takes this expression where R is a baryon to photon density ratio, which grows like A, simply because this goes like A to the minus 3, and this like A to the minus 4. So the sound speed will go to 0 at the beginning of matter domination, and the consequence will be a damping of the propagation of acoustic wave that will not be super important for us. So now we cleared the role of pressure forces in our photon baryon fluid. Now comes the role of gravity. And the most obvious role of gravity is contained in this factor, which is like the Laplace operator of the gravitational potential. So then, in the same way as we had the Laplacian of pressure, here we have the Laplacian of a gravitational potential. Obviously, this will account for gravity forces. Gravity forces can confine our fluid in potential well, and so impact the evolution of the temperature fluctuation. So gravity forces will always compete with pressure force because they want to concentrate matter and pressure wants to resist to compression. Why is there a 3? Well, in the full equation, everything is multiplied by 3. The 3 is here, but we divide it by 3. That's why we have this denominator. It's not important. Okay, gravity forces. Next term connected to gravity. We have here a term which is related to the scale factor. So this term related to the scale factor has to do with the expansion of the universe and with the fact that the expansion stretches distances between particles. This stretching of distances make gravitational force less efficient because gravitational force go like 1 over square distance between particles. So this term is a term that modulates the impact of gravity force, and it's multiplied by a coefficient r, because at early times, photons dominate, gravity forces are not very important. At late times, baryons dominate, gravity forces are important. So all in all, this is called the baryon damping term, and it's important at late time when baryons are important. This term has the same structure, but now the expansion rate is multiplied by a phi prime. It is a local modulation of this effect due to the fact that phi is a local modulation of the scale factor. And finally, the last term is very obvious. It's a dilation term. It just tells you that if you are in a place where there is more expansion, then locally you dilute your photons more, so you redshift them, and this will have directly an impact on the evolution of the density theta 0 in this point. So these are all our terms, pressure terms and gravity terms, and they all influence the evolution of theta 0. Now that we understand this equation, we can try to find approximate solutions. Before that, we can guess what is the type of solution. The solution, as we said, will be oscillatory. The fact that there are gravity terms means that this oscillation will be modulated in a subtle way by gravitational effects. Okay. We can try to guess around which value theta 0 will oscillate. If we had only the pink term, clearly it would oscillate around 0. But we see that if we have a gravity force, this will shift the equilibrium point of the oscillation. So suppose that I want to see what is the equilibrium point, or if you want, the inflection point in my oscillatory solution for theta 0. Then I can take everything to be static. I can neglect all the derivatives and look at just the equilibrium relation given by equating the two terms that carry no derivative. And when you work a bit with just this equality, you find a solution, theta 0 equilibrium, which is -1 plus r psi. Psi is a gravitational potential, and r is our baryon to photon density ratio. So we see that this term is going to shift the equilibrium point of the solution, and this equilibrium point comes from the competition between gravity and pressure. If we had only pressure, we would have a symmetric solution. If we have gravity also, we tend to favor regions in the universe with overdensities with respect to regions with underdensities. And in Fourier space, this shows up as a shift of this equilibrium point. And this will be very important later on at some point to understand one very nice effect in the shape of the CMB spectrum. You could solve this equation with an approximate analytic solution using the WKB formalism. You would get some oscillation, as we said, with a cosine, with some arguments here. And in front of the cosine, you have an amplitude. The amplitude tends to decrease when r increases. This comes from the fact that we said when baryons are more and more important, r increases, the sound speed decreases. This is why you get a damping of the solution. And then the solution oscillates not around 0, but around our equilibrium point. So this is a nice approximation, and you can try even to compute the full CMB spectrum using this approximation. It gives you something reasonable. What this solution neglects are two things. To get to this solution, you need to neglect the last two terms with the time variation of the metric, which is called a gravity boost contribution. We will study it later. And you need also to buy this tight coupling approximation. And when you buy the tight coupling approximation, when you say that photon is in tight coupling until decoupling and then is completely decoupled, what do? You neglect the photon diffusion effect that we reviewed this morning. The fact that the photon mean free path increases gradually from 0 to infinity. So up to these two effects, you get here a solution which gives a good hint of the shape of the CMB spectrum. Why do I call the fact of neglecting these two terms, neglecting the gravity boost? The gravity boost is the fact that when we will solve the full exact equation. If there is a regime in which phi varies with time, then this derivative will be non-zero. There will be a driving term in our driven harmonic oscillator, and this will increase the amplitude of the fluctuations. And we will see that there exists such a time, and this will cause the famous gravity boost of the acoustic oscillations. Okay. It's a lot of information, but CMB physics is a very rich topic, and I'm already simplifying a lot. But you will see that all this will assemble nicely at some point, and if you do the effort of following each step in my discussion, at the end, you should have a very clear understanding of the detail of the CMB CL shape. Okay, let's discuss a little bit more this argument here. If the sound speed was a constant, the argument of my cosine would be just k cs eta. And we will see that this quantity has to do with a comparison with the wavelengths of the mode with what we will define to be the sound horizon. This will come later. But because my cs is not a constant, my WKB solution gives me this integral here. So I will explain the meaning of this argument later on. Now what I want to do is to show you how the solution of this equation evolves with time. And here I took the solution from class without any approximation. So it's not using the tight coupling approximation, and it has all effects included. But still, now that we know the tight coupling solution, we will understand the full solution. So I will have plots with two axes in this part of the lecture. Here, I have conformal time going from the early universe until today. In conformal time, the conformal age of the universe is around 12,000 megaparsecs. So this is the time, this is not the time today, sorry, the time today is later on. Here, I have cut my plot at some time after recombination. And in fact, here I have some characteristic time, which are the time of equality between radiation and matter, and the time of recombination. Recombination takes place at the beginning of matter domination, so it takes place after the time of equality. Now I choose to look at a given mode K. This is just an arbitrary choice. We could do a plot for other modes. And for this mode K, I try to see how different fluctuations evolve with time. And I start by describing the evolution of my metric fluctuation. I know that initially my metric fluctuation is related to the curvature perturbation by using the Einstein equation on super Hubble scales. And if I use the adiabatic initial condition, where there were some funny numerical factor, if I normalize my transfer function for psi to r equal 1, then I should normalize my initial psi to 2/3. So I start from 2/3. For this particular mode, Hubble crossing will take place when k eta is equal to 1. For a k of 1/2, this Hubble crossing corresponds to the red line here. Well before Hubble crossing, I have a constant solution for psi in agreement with the fact that in the Newtonian gauge, super Hubble solutions are frozen. But then I see that when I approach Hubble crossing, my metric fluctuation is damped. And it even has small oscillations here, but they're not too interesting. What is interesting is the fact that for this mode, at least, the metric fluctuation gets damped when you approach the Hubble crossing line. And we may wonder why. It's like if the gravitational potential would be smeared out. In fact, it is smeared out during radiation domination and in scales comparable to the Hubble scale or smaller because of the role of photon pressure. Photon pressure wants to smear out fluctuations, and this will cause this decrease of the metric fluctuations. And if you want to see how this is possible, you can do some power counting in the Poisson equation. So let me write my Poisson equation, which gives me the relation between metric fluctuation and density fluctuation on sub-Hubble scales. Now I am interested in sub-Hubble scales. I look at a universe dominated by radiation such that the total density fluctuation is the one coming from relativistic species. And then my Poisson equation says that the Laplacian of phi is 4 pi j, a square, which comes from the fact that I've moved the a square from here to the right, times delta rho of relativistic species. To understand how phi or psi, I take them as equal, evolve with time, I should look at the time evolution of delta rho r. I expand delta rho r as a background radiation density times the relative density fluctuation of radiation. And now I have three terms which may depend on time. I have my scale factor squared here, which came from the physical Laplacian. Rho r goes like a to the minus 4, because this is the density of radiation. And I understand that delta r should be experiencing oscillations. But the acoustic oscillation are oscillations within an envelope which is roughly static. The acoustic oscillation cannot get amplified because photons have pressure. Pressure doesn't want to create big density contrast. It reacts to density contrast. And so typically when you have a propagation of sound wave in a medium with some pressure, the amplitude of the sound wave is either constant or even experiencing dissipation, but is not increasing. So if I consider that delta r has oscillation within a constant envelope and I average over one period, then I can consider that delta r has a constant amplitude, and I write a to the power 0. And overall, I have an a to the minus 2, and it shows me that on sub-Hubble scale, my metric fluctuation must decrease during radiation domination. Again, this is because of photon pressure. It would be very different if I was looking at fluctuation on sub-Hubble mode during matter domination. In this case, I would write again my Poisson equation with here a delta rho total that would be dominated by matter. I would expand my delta rho m of non-relativistic matter into the homogeneous density times the relative fluctuation. And then I would say that I have a factor a square, that my rho m give us an a to the minus 3. And for delta m, I would still need to solve an equation of motion. But if you have done a little bit of study of structure formation, you probably know the answer. When structure form during matter domination, at the level of linear perturbation theory, the density contrast of matter grow proportionally to the scale factor, like a power a to the 1. And now when you count the different powers, you see that they cancel out and that phi is a constant. This means that during matter domination, on sub-Hubble scale, you have a very subtle cancellation between the effect of gravitational clustering that would like to increase density contrast and also in the metric fluctuations, and the expansion of the universe, which is ironing out everything and which tends to decrease the density contrast in the metric fluctuation. During matter domination in linear perturbation theory, the two effects nicely cancel each other, and phi is found to be constant on sub-Hubble scales. So here we were looking at a mode crossing the Hubble radius during radiation domination, because the red line is before the equality line. And that's why the metric fluctuation went to 0. If I would look at a mode with a much smaller k, a much larger wavelength, then maybe this mode would cross the Hubble radius during matter domination. And then because of phi being constant, it would keep a constant value